So in the last video, we looked at Euler paths and Euler circuits, and the question, as we kind of close with, says, so if you've got a graph, does it have an Euler path and an Euler circuit automatically? Turns out some do and some don't, and this thing called Euler's theorem will allow us to tell if it does have one. A path or a circuit without first searching to find one, because as the graphs get more complicated, the first ones we looked at were fairly simple, but as they get more complicated, it can be actually kind of tough to tell without spending a whole lot of time trial and error. So Euler's theorem is stated as follows. If all the vertices are even, if all of them are even, then it does have at least one Euler circuit, and then obviously that's also a path. And so that circuit can start at any vertex. If, and this is weird, but this is the way it turns out, if exactly two of the vertices are odd, and remember the difference, odd and even vertices, that has to do with the number of edges that leave it. So in other words, the number of lines that leave a given point. So if there's an odd number of lines leaving a point, then we call that vertex odd. So if there are exactly two odd vertices, then it will not have an Euler circuit, but it does have at least one Euler path. And to make it work, the path must begin at one of the odd vertices and end at the other. So that gives you some strategy in terms of what to do. If there are more than two vertices that are odd, then it has no path or no circuit. No Euler path, no circuit. So that actually kind of is nice just for ruling things out. And that's really all this example is. This is a question we'll practice on ALEKS. But it's just really a matter of reading that theorem and then deciding. So you've got, and I'll kind of scroll back and forth. If you've got no odds and 17 evens, then here we're supposed to, applying Euler's theorem, we're supposed to determine whether it has an Euler circuit, an Euler path, but no Euler circuit, or neither. So which of these are we going after? And if you know that you have a connected graph, and by the way, that little word gets overlooked sometimes, so it's got to be connected. If it's not connected, then obviously you can't draw a line to connect the points, draw a line to connect the vertices. So it's got to be connected. So if you have a connected graph with no odd vertices, that means they're all even. So 17 of them are even. Then you're looking at number one. So by number one, in Euler's theorem, then we have at least one Euler circuit. So we know we have an Euler circuit there. If you have 18 odd and 5 even, well, if there's more than two odds, then you don't have either one. So this one's definitely neither by number 3. You have neither. You don't have an Euler path or an Euler circuit. And here we've got a connected graph with exactly 2 odd and 8 even. That one is number 2. So by number 2 in Euler's theorem, we have an Euler path with no circuit. So all that tells us, just so you're keeping the idea here, all this information and applying Euler's theorem, all that tells us I think we say this later, but it's like an existence theorem. That's what a mathematician would say. It just tells you that one exists. It doesn't tell you how to find it. It doesn't tell you what it is. It just says, yeah, there is one. So if we can use that information just to determine whether or not there is an Euler circuit or an Euler path, that's what Euler's theorem lets you do.